Our observations of superposition for sinusoidal functions have thus far been a special case of superposition that results in a standing wave. As you can see in this demo, the resulting wave, the sum of the two waves, does not move in space. Unlike the two waves that are added together, which move to the left or the right, the sum stays in one place while the amplitude varies as the time is incremented. In general, superposition does not result in a standing wave. In order to see more general types of superposition, we will vary the parameters of wave 1 and wave 2. Let's start by adjusting the amplitude. Change the amplitude of wave 2 to 2. And see what happens to the graph. The peaks and the troughs of the waves still line up, as in the standing wave case. But now we do not observe complete destructive interference when the two waves are out of phase. When the waves overlap completely, we see constructive interference occurring again. The resulting amplitude of the sum is 3, the amplitude of wave 1 plus the amplitude of wave 2. It is also interesting to note that when observing the superposition, the amplitude seems to oscillate. In fact, this variation from its maximum at 3 to its minimum at 1 can be described by a sinusoidal function. Now, let's change the amplitude of wave 2 back to 1 and vary some of the other parameters. First, change the wavelength of wave 1 to 1 and observe what happens. Now, wave 1 has twice as many peaks and troughs as wave 2. Can you predict what will happen as we increment the time? Let's try to line up the two waves as we did before when we observed constructive interference. Notice that when the peak of wave 2 and the peak of wave 1 line up, the amplitude of the sum is still 2, the amplitude of wave 1 plus the amplitude of wave 2. However, now that wave 1 has two wavelengths for every one wavelength of wave 2, lining up the maximums also lines up the minimums. Therefore, in one wavelength of the sum, we observe instances where the two waves interfere constructively and instances where the two waves interfere destructively. This results in the wiggly shape we observe. Let's try changing the wavelength of wave 1 to 0.5. Based off of our previous analysis, what do you think will happen? In this case, it may appear more apparent that the superposition is the sum of the two waves. Again, because the wavelengths are different, the two waves do not line up exactly, and so we don't observe a standing wave. However, there are instances where individual maxima and minima of the two waves line up. Change the wavelength of wave 1 back to 1, and change the amplitude of wave 2 to 2. Can you predict what will happen to this superposition? Lastly, we will modify the equation for wave 2 so that both waves travel in the same direction. Simply change the minus sign, subtracting the wave speed in the counter, to a plus sign. Drag this new equation down to the last entry. Now set the wavelength of wave 1 to 2 and the amplitude of wave 2 to 1. Notice that when we increment the time, both waves travel together and are exactly in sync. Let's change the phase constant of wave 1 to pi over 3 and observe what happens. Now wave 1 is out of phase from wave 2 by pi over 3 radians, but the two waves continue to travel together, keeping the phase difference constant. Continue to experiment with these parameters until you are comfortable in your understanding of superposition for two waves.